and then started second topic now. So first we are started synthesis of nanomaterials. Synthesis of nanomaterials, we given the particles, the nanoparticle synthesis and division is over yesterday's class. Next, physical methods. In the first one, high energy ball milling is over, and physical vapor deposition (PVD) is started. In physical vapor deposition process, the workpiece is subject to plasma bombardment. There are different methods of physical vapor deposition is used. The method are evaporation, sputting, ion planning, the laser ablation. Evaporation. In evaporation, the substrate is placed inside a vacuum chamber in which a source of material to be deposited is also located. The source material is then heated to the point where it starts to boil and evaporate. The vacuum is required to allow the molecules to evaporate freely in the chamber, and they subsequently condensed on all surfaces. This principle is same for all evaporation technologies. Only the method used to the heat evaporate the source material differs. So in that first, this figure also yesterday we completed glass ball jar, substrate table, crystal detector, substance holder and sample, path of vapor, clamps connected to the connected to high current source, filament board filled with evaporant like that. Ionized cluster beam deposition. Nanoparticles can be made by decomposing solids at high temperature having metal cations, cations and molecular anions or metal organic compounds. The process is called thermolysis. Small lithium particles can be made by decomposing lithium azide. Li-N3, the material is placed in an evaporated quartz and heated to 400 degrees centigrade in the aperture. At about 370 degrees centigrade, the Li-N3 decomposes, relaxing N2 gas, which is observed by an increase in the pressure on the vacuum gauge. In a few minutes, the pressure drops back to its original value, indicating that all the N2 gas has been removed. The remaining lithium atoms coalesces to form small colloidal metal particles. Particles less than 5 nanometer have been made by this method. Now, what it is my sample in TA foil furnace, evacuated quartz tube. The figure is like this: molecular pump, 4-pump, vacuum gauge, all these. So what it is? Production of nanoparticles by them thermolysis. Production of nanoparticles by thermolysis is like this. Here, vacuum gauge, molecular pump, 4-pump, evacuated quartz tube, furnace. In between, we have the sample in TA foil. So here, what it is? Sputting or laser evaporation. Here, what it is? Sputter means to split out or throw out the sputting in a process in which surface atoms are physically ejected from the surface of momentum transfer from an energetic bombarding beam, say laser beam. Next, shows a laser evaporation sputting to get atmosphere. A high intensity laser beam is allowed to incident on target metal disk. This causes the evaporation of atoms from the surface of metal. The atoms are then swept by a burst of helium into vacuum chamber through an orifice. The expansion of gas in vacuum chamber produces a cooling because it has passed through orifice. Now the clusters of metal atoms as nanoparticles are formed a vacuum chamber. So sputtering or laser evaporation is showing like in this figure. Here how it is explanation we are giving. A high intensity laser beam is allowed to incident on target metal disk. This causes the evaporation of atoms from the surface metal. The atoms are then swept by a burst of helium into vacuum chamber through an orifice. The expansion of gas in vacuum chamber produces a cooling because it has passed through orifice. Now the clusters of metal atoms as nanoparticles are formed in vacuum chamber. Next, chemical methods. Solution, SOL gel method and colloidal method. SOL gel is a chemical process used to make ceramic and glass materials like the form of thin film fibers or powders. A soil is a colloidal or molecular suspension of solid particles of ions in a solvent. A gel is a semi-rigid mass that forms when the solvent from the soil begins to evaporate and the particles of ions left behind begin to join together in a continuous network. SOL gel process consists of the desired colloidal particles, one dispersed in a liquid or a foam soil. The deposition of solution produces the coating on the substrate. The particles in the soil are polymerized through the removal of stabilizing components and produces gel in a state of continuous network. The final heat treatments fertilize the remaining organic and inorganic compounds and form an amorphous or crystalline cooling solid gel. Formation occurs in hydrolysis, condensation, groups of particles, and agglomeration of particles. Agglomeration of particles. These are the chemical method. First one, sol gel method and colloidal method. Here we are discussing about the consists of 4 properties. Next one, hybrid method. So schematic representation of sol gel process of synthesis of nanomaterials is shown in figure. Here how it is deviated one to another one given in figure. Here what it is, precursor, solid, next gel, and then rapid drying aerogel, and then structure organic, then it is golden powder, like that. Schematic representation of sol gel process of synthesis of nanomaterials is like this. Next, hybrid material. Hybrid method. Hybrid materials are consist of 2 consistent the nanomaterials. Nanometer or molecular level. Commonly, one of these compounds is inorganic and the other one organic in nature. Thus, they differ from the traditional composites where the constituents are at the macroscopic and micrometer or to millimeter level. Mixing at the microscopic scale leads to a more homogeneous material that either show characteristics in between the 2 original phases or even new properties. Introduction. Hybrid nanoparticles are expected to have larger application in biomedicine and antibacterial, energy storage, electronics, and catalysis than single nanoparticles. In general, the synthetic methods could be classified into 2 main categories. First one, physical and chemical methods. As compared to the chemical methods, the synthesis of hybrid nanoparticles by physical methods are simple, but the control of this size hybrid nanoparticles seems to be complex. Regarding the chemical synthesis, especially the controllable monostructural, they are expected to provide a better performance than that obtained from physical methods. In the physical preparation methods, the individual nanoparticles remain sometimes separate and distinct with the final nanostructure. However, a direct and stronger hybridization between nanoparticles is often obtained by this pathway, while the nanoparticles prepared by chemical method can exhibit unwanted properties due to the presence of chemical species such as the stabilizing ligands, polymer shells. Different methods have been employed for the as compared to the chemical methods. Hybrid parameters. Hybrid method we are given is regarding the chemical synthesis, especially the controllable nanostructural. They are expected to provide a better performance than that obtained from physical method. In the physical preparation methods, the individual nanoparticles remain separate and distinct within the final nanostructure. However, a direct and stronger hybridization between nanoparticles is obtained or often by this pathway, while the nanoparticles prepared by chemical method can exhibit unwanted properties due to the presence of chemical spices, such as the stabilizing ligands, polymer shells. Different methods have been employed for the fabrication of hybrid nano carriers depending upon their chemical composition and applications. First is two-step approach process in which the inner core and outer shell are prepared separately and then incubated for formation of hybrid nanoparticle. So the second approach in the single step in which various state-of-art techniques of the self-assembling are being incorporated. Next, conventional two-step method. It was the first technique employed for the fabrication of hybrid carriers. Here, the inner core and outer shell components are prepared in two separate steps, employing suitable polymers and chemicals, and are then combined to form the hybrid nanoparticle. The foremost type of core shell hybrid nanoparticle contained a core of the polymeric nanoparticles and an outer shell of performed lipid components such as liposome or lipoparticles in appropriate ratios. The single step method. The single step method is applied when the core materials such as polymer, silica, and organic substances are miscible with the drug load and also solubilized in the organic solvent. The double emulsion stop is employed when the compound is immiscible with the organic solvents and does not form covalent linkage with the core material. As this method requires multiple steps for mixing of different components, hybrid nanoparticles are produced. Different components relatively larger hybrid nanoparticles are produced. Further, any of the suitable techniques such as ultrasonication or extraction by high pressure homogenization also reduces the particle size as the polymer solution is passed through the nozzle under high pressure. Electrochemical method and chemical vapor deposition method. Electrochemical method and chemical vapor deposition method. In this method, a substrate is prepared with a layer of metal catalyst particles such as nickel, CO, or iron. And the substance is approximately 700 degrees centigrade in a chamber. To initiate the growth of the nanotubes, two gases are blown into the chamber. One is a process gas such as ammonia, nitrogen, or hydrogen, contains one carbon atom containing gas methane. The high temperature in the chamber breaks the bonds between the carbon atoms and the hydrogen atoms in the chamber. This results in carbon atom with no hydrogen attached. These carbon atoms attach to the catalyst particles where they bond other carbon atoms. This results in the formation of a nanotube. Here, but it is substrate, furnace, vacuum pump, end-to-end methane. Therefore, a schematic of a typical chemical vapor decomposition reactor. Next, electrodeposition. It is used to electroplate a material. In many liquids called electrolytes, when current is passed through two electrodes immersed inside the electrolyte, certain mass of the substance liberated at one electrode gets deposited on the surface of the other. By controlling the current and the other parameters, it is possible to deposit even a single layer of atoms. Nanostructured films of copper, platinum, nickel, argentinium, etc., AU, etc., can be produced by electroposition. Electrodeposition. The films thus obtained mechanically robust, highly flat, uniform, and have large surface areas. They exhibit quite different and favorable electrical properties: current source, cathode, anode, magnetic bar, playing vessel, and thermometer. So, schematic representation of electrodeposition method of synthesis of nanostructure films is shown in this one. So, here, what are the physical methods of nanomaterials? What are the chemical methods of nanomaterials? What is necessary in total summary? Nanomaterials can be fabricated two approaches: top down, in which we go from larger to smaller perspective, and bottom up, in which we go from simple to complex perspective. So first one is top to down, means which we go from larger to smaller perspective, and bottom up, in which we go from simple to complex perspective. So the top down process, therefore, in the top-down process of synthesis, there is no control over the size and the morphology of the nanoparticles. Ball milling method, solution gel in an important method of nanoparticle synthesis belonging to bottom-up method. Next, high-energy ball milling, physical vapor deposition, ionized cluster beam deposition, sol gel method and colloidal method, hybrid method and electrochemical method, and chemical vapor deposition. All these are the different questions in this particular lesson. Next, model examinations questions. What we have discussed about the chemical methods of nanomaterials, write about physical methods of nanomaterials in detail, and explain ball milling method and sol gel method and sputter deposition method. So after that, we go for remaining books. Material science. Next, third lesson is characteristics techniques. Here, characteristics techniques, what we are studying: X-ray diffraction, XRD analysis, UV visible spectroscopy, and IR spectroscopy, and applications of electron microscope. SEM means scanning electron microscope, and TEM means important for this lesson, transmission electron microscope, and AFM means atomic force microscope. So what is the introduction for this characteristic techniques? Means spectroscopy is the branch of science that deals with the study of interaction of matter with light. Interaction of matter with light, we are studying the spectroscopy. The principle is based on the measurement of spectrum of a sample containing atoms, molecules. Spectrum is a graph of intensity of absorbed or emitted radiation. This principle is based on the measurement of spectrum of a sample containing atoms, molecules. Spectrum is a graph of intensity of absorbed or emitted radiation by sample versus frequency mu of wavelength lambda. Spectrometer is an instrument designed to measure the spectrum of compound. Absorption spectroscopy. It is an analytical technique with the concerns with the measurement of absorption of electromagnetic radiation. So what it is, the principle based on the measurement of spectrum of a sample containing atoms by molecules. Spectrum is a graph of intensity of absorbed or emitted radiation by sample frequency mu or wavelength lambda. Spectrometer is an instrument designed to measure the spectrum of compound. Absorption spectroscopy. It is analytical technique which concerns with the measurement of absorption of electromagnetic radiation. It is an analytical technique which concerns with the measurement of absorption of electromagnetic radiation. Now, example, UV 185 to 400 nanometer, visible 400 to 800, and spectroscopy, IR spectroscopy 0.76 to 50 micrometer. Emission spectroscopy, it is an analytical in which emission is according to some property of the emission and the amount of dispersion is measured. Example, mass spectroscopy. Characterization of nanoparticles. Characterization of nanoparticles. XRD analysis or X-ray diffraction. Here what it is, a typical XRD pattern of indium oxide nanoparticles prepared by the chemical method. The XRD study indicates the formation of the indium oxide In2O3 nanoparticle. So that from this study, considering the peak of diffraction angle of 450 average particle size has been emitted by using Debye formula. D is equal to 0.89 lambda by beta cos theta, where lambda is wavelength of X-ray of 0.1541 nanometer copper oxide radiation. Beta is FWHM, full width of half maximum 0.011 radian. Here theta is the diffraction angle 30 degrees and D is the particle diameter size. The average particle size is calculated to be around 12 nanometer. Thus, using XRD pattern, we are able to calculate the particle size. XRD particles of nanocrystalline In2O3 samples using gum calculated calcined in air for 2 hours. UV visible spectroscopy principle. The UV radiation region extends from 10 nanometer to 400 nanometer. And the visible radiation region extends from 400 nanometer to 800 nanometer. So here the near UV region 200 nanometer to 400 nanometer, far UV region below 200 nanometer. So that for UV radiation spectroscopy is studied under vacuum condition. The common solvent used for preparing sample to be analyzed in either ethyl alcohol or agent. The possible electronic transitions can graphically shown in anti-bonding, non-bonding, bonding, and bonding. Here is sigma to sigma. Sigma electron from orbital is excited to anti-bonding orbital sigma. The energy required is large for this transition. Example, methane has CH bond, undergoes sigma transition and shows absorptions maxima at 125 nanometer. Like that, pi electron is bonding is excited to pi star. Alkanes generally absorbed in the region 170 to 205 nanometer, and the transition requires less energy than sigma to sigma transitions. Example, saturated compounds containing atoms with lone pair of electrons like oxygen, nitrogen, sulfur, and halogens, and the peaks in UV region is small, 1 to 2 nanometer. Next, N2 pi star, an electron from non-bonding orbital is promoted to pi star orbital. It compounds containing double bond involving heteroatoms C is equal to 0, C triple bond N and N triple double bond U undergo the transition. Such a transition and show absorption at longer wavelength 300 nanometers. Sigma to pi star and pi to sigma star. These transitions are forbidden transitions accessible to UV visible. The terms used in UV visible spectroscopy are chromosphere. The part of molecule responsible for imparting cold are called as chromospheres. Example, NO2, N double bond O, C double bond O, C double bond N, C triple bond N, C double bond S, and C double bond C, etc. To interpret UV visible spectrum, non-conjugated alkylanes show an intense absorption below 200 nanometer and are therefore inaccessible to spectrometer, and non-conjugated carbonyl group compound give a weak absorption band in 200 to 300 nanometer region. So that what it is, next continuation is Oxochrome, the functional group with non-bonding electrons that does not absorb radiation in near UV region, but when attached to a chromopore alters the wavelength and intensity of absorption. Benzene, lambda minimum is equal to 255 nanometer. Phenyl, lambda maximum is equal to 270 nanometer. And aniline, uh, lambda maximum is equal to 280 nanometer. Therefore, the absorption and intensities are classified as first one, bathochromic shift, hydrochromic shift, and hyperchromic effect and hypochromic effect. So in that absorption magma, the absorption when absorption magma lambda maximum of a compound shifts to longer wavelength is known as redshift. Example, OH, OCH group exhibit redshift. Next, when lambda maximum of a compound shifts to shorter wavelength, it is also as blue shift. It is due to the presence of a group which causes removal of configuration or by the change of solvent. Aniline shows redshift in acid medium. Next, hyperchromic effect. When absorption intensity epsilon of a compound is increased, it is known as hypochromic shift. Example, pyridine, and if it is decreased, it is known as hypochromic shift. Naphthalene, hypochromic effect is not there. Hypochromic shift, blue shift, red shift, and hypochromic shift. Up and down, it shows what it is absorbance. Applications, qualitative and quantitative analysis. Visible spectroscopy, it is used for characterizing atomic compounds. It can be used to find overall concentration of the solute and study. Now, detection of impurities. It is one of the important methods of detecting impurities in organic solvents. Detection of isomers are possible. Molecular weight can be used by using fluids in spectroscopy. Infrared spectrum, it is an important record which gives sufficient information about the structure of a compound. In an unlike UV spectrum, which consists of relatively few peaks, this technique provides a spectrum containing a large number of absorption bands from which we can get the information about the spectrum of a material. The absorption of infrared radiation causes the various bands in the molecule to sketch the band with respect to another, and the molecular vibrations in the order 2.5 micro to 15 2.5 micrometer to 15 micrometer can be detected in the IR spectrum region. Therefore, the IR spectrum region, the region from 0.8 mu to 25 mu is called near IR, and that from 15 micrometer to 20 mu is called far IR region, and the characteristic stretching absorption band appears above 1500 per centimeter. Principle of IR spectroscopy. Absorption of IR spectroscopy. Radiation causes from a lower to the higher vibrational level. The IR spectra is a vibrational rotational spectra. All the bonds in molecule are not capable of observing infrared red energy, but only those which are accompanied by a change in dipole moment will absorb in the absorbing infrared region will absorb in the infrared region. Such vibrational transitions which are accompanied by a change in the dipole moment of the molecule are called infrared active transitions. Thus they are irresponsible for absorption of energy in the infrared region. When infrared light is passed through the sample, the vibrational rotational energies of the sample beam source and detector reference and motor amplifier spectrum, and it is having the wavelength region is 67 centimeter. Stretching. In this type of vibration, the distance between the two atoms increases or decreases, but the atoms remain in the same bond. But the atoms remain in the same bond. There are two types of stretch vibrations. Simple stretching. The movement of the atoms with respect to a particle atom is a molecule in a molecule is in the same direction. Asymmetric stretching. In this vibration, one atom approaches the central atom while the other departs from it. Bending. In this type of vibration, the positions of the atoms charged with respect to the original bond consists. Bending vibrations are of four types: scissoring, rocking, wagging, and twisting. In the vapor state, the absorption band for stretching a particular bond occurs at the highest wave number compared to that when the substance is in the liquid state, which in turn occurs at high wave number when the same substance is in the solid state. Instrumentation. Infrared light radiation from the source is split into two beams. One of the beam is passed through the sample under examination is called sample beam. Is called the reference beam. When the beam passes through the sample is less intense due to the absorption of certain frequencies. Now there will be a difference in the intensities of the two beams. Let I not be the intensity of let I not be the intensity of the reference beam and I be the intensity of the beam. After interaction with this, after interaction with the sample respectively, the absorbance of the sample at a particular frequency as A is equal to log I naught by I and transmittance is I by I naught. Therefore, A is equal to log I by intensities of the bands can be recorded as linear function T against the corresponding wave number. Intensity of the two beams are converted into and measured as applications of IR spectroscopy, identification of an organic compound, structure determination, qualitative analysis of functional graphs, distinction between two types of hydrogen bonding, qualitative and quantitative analysis, study of chemical reaction, study of keto and torism and complex molecules for determining the conformational analysis, detection of impurity in a compound and rotational isomerism. Applications of electron microscopy, scanning electron microscope, transmission electron microscope, atom force microscope, scanning electron microscope, light source, slit, condensing lens, objective lens, magnified image, protection lens, final image, scanning electron microscope, image, magnetic protection lens, magnified image, magnetic objective lens, magnetic condensing lens, object and electron gun. The image in scanning electron microscope, the image is produced by scanning the sample with a focused electron beam and detecting the secondary backscattered electrons. Electrons and photons are emitted at each beam location and subsequently detected. The schematic representation of SEM is shown in figure. The electron gun produces a stream of monoatomic electrons. The electron stream is condensed by the first condenser lens. It works in connection with the condenser aperture to eliminate the high angle electrons from the beam. Next, the second condenser lens forms the second condenser lens forms the electrons into a thin light coherent beam. Object aperture eliminates high angle electrons from the beam. A set of coils acting on electrostatic scans and sweeps the beam in fashion. As in TV, the beam dwells on points for a period of time determination by the scan speed. Is in this range. The objective lens focuses the scanning beam onto the part of the specimen. Next, when the beam strikes the sample, interaction occurs before the beam moves to the next well point. The various instruments housed to measure various interactions count the number of interactions and display a fixed and CRT. Instrument focus to measure the various interactions, count the number of interactions, and display a fixed on CRT. The intensity of display is determined by the interaction number. More interactions given, brighter fixed. The process repeated until the grid scan is finished and then repeated. The entire pattern can be scanned 30 times per second. SEM gives useful information. One is topography, second one is morphology, and third one is composition, fourth one crystallographic information. SEM gives useful information on topography, morphology, composition, and crystallographic information. Transmission microscope is a schematic representation of time show figure. Each labeled functions are explained below. The electron gun produces stream monochromatic. A schematic term shown in figure. Each part is labeled and their functions are explained below. The electron gun produces a stream of monochromatic electrons. This stream is focused to a small coherent beam for the first and second condenser lenses. The condenser aperture knocks the high angle electron. The beam strikes the specimen. The transmission portion focused by the objective lens into an image. Objective aperture enhances the contrast by blocking out high-angle diffracted electrons. Selected area aperture enables to example the periodic diffraction of electrons by an ordered arrangement of atoms in the sample. Intermediate and protector lenses enlarge the image. The beam strikes the phosphor screen and image is formed on the screen. The darker areas of the image represent thicker, denser sample areas since these lesser electrons. Lesser electrons, the brighter areas of the image represents thinner or lesser dense sample areas since these areas transmits more electrons. AG nanoparticles studied using XRD. AG nanoparticles are spherical in shape with a smooth surface morphology. The diameter of the nanoparticles is found to be approximately 15 nanometer. image shows the produced nanoparticles are more or less uniform in structure, shape. Image of the nanoparticles. SEM. So a spectrum objective object camera flow screen monitor and computer scanning shell. AFM, atomic force microscope. Atomic force microscopy is used to investigate the electrically ion conductive materials like proteins. In 1986, Binning and also demonstrated for the first time the ideas of AFM, which is an ultra small probe at the end of a cantilever. In 1987, the Ram Singh et al. Developed an AFM setup with a Veterano cantilever technique, which is used the light level mechanism. The intrinsic adhesive between tip and sample. There is another one from the capillarity net condensing between the tip and water meniscus interface and the interface from the humidity. Here, what it is R1 to R2. Electromagnetic interaction between tip and sample. Electromagnetic interaction is caused by both the localized changes and the polarization of the substrate due to the potential difference. It has been used to study electrostatic properties of samples such as charges and insulator surfaces of ferroelectronic domains. Magnetic interaction. It is caused by magnetic dipoles both on the tip and the sample. Magnetic interaction. It is caused by magnetic dipoles. It is caused by magnetic dipoles both on the tip and the sample. Contact mode and dynamic mode. In contact mode, the deflection of the cantilever is kept constant. Contact mode AFM consists of raster scanning, raster scanning, and the prober sample while monitoring the change in cantilever detection of the split photodiode detector. A feedback loop maintain a constant cantilever deflection by vertically moving the scanner to maintain a consist photo detector different signal. The distance scanner moves vertically at each XY data point. XY data point is detector difference signal. The distance scanner moves vertically at the XY data point is stored by the computer to form the topographic image of this. This feedback loop maintains a constant force during minutes, which uses a sharp tip to raster scan can image the surface topography with extremely high magnification, up to 1 lakh times comparable to or even better than electron microscope. Measurement of an AFM is made in 3 dimensions. The horizontal XY plane and the vertical Z dimension. Resolution magnification at Z direction is normally higher than XY plane. atomic interaction at different tip scale distances, repulsion. At very small tip sample distances, a few atoms, a very strong repulsive force appears between the tip and the sample's atoms. Its origin, it is a so-called exchange interactions due to the overlap at the electronic orbitals at atomic distances. When this repulsive force is predominant, the tip and sample are considered to be in contact. Attraction, polarization, interaction between atomic and instantaneous polarization of an atom in polarization in nearby atoms, and therefore an attraction takes place. Different modes of tip sample interaction when in contact friction. The cantilever bends laterally due to the friction force between the tip and the sample surfaces. Adhesion can find as free energy change to separate unit area of two media from contact to infinity in vacuum or in a third medium. In general, care has to be taken with the term adhesive, since it is also used to define force, the adhesive force. Sample constant force mode. Two contact scanning modes, constant force and constant height mode. Constant force mode is this one, and constant height mode is this one. Next, constant force, constant height differences, and what are the advantages for constant force is large vertical range. Constant force can be optimized to the maximum. And advantage, simple structure and fast response. Disadvantages, requires feedback control and slow response. Next, disadvantages, limited vertical range, cantilever, bending and adhesive dynamic and bending and detector dynamic range and varied force. Dynamic mode. In dynamic mode, the tip is oscillated in the resonance frequency, and the amplitude of the oscillation is kept constant. Amplitude of the oscillation is kept constant. Trapping mode, imaging. It takes the advantages of the contact and dynamic mode. It eliminates frictional forces by intermittently contacting the surface and oscillating with sufficient amplitude to prevent the tip from being trapped by adhesive meniscus forces from the component layer. Next, AFM can work in liquid environment. A key point for liquid AFM is transparent solid, usually glass surface, which together with the solid sample is retained to a liquid environment, which maintains stable optical paths for the laser beams. An optical O-ring can be used to form a big sealed liquid cell. Otherwise, the system can be as work as an open all fashion. And then summary, what we are studying in this next: quartz glass body, light, cantilever block, solvent, sample, ring. So here advanced imaging techniques, AFM, advanced imaging techniques for AFM is lateral force microscope, modulation microscope, and trapping mode scanning. Summary, samples, SEM-TEM must be conductive, AFM, insulating conductive, magnification 2-dimensional for SEM-TEM, AFM 3-dimensional, environment, vacuum, air, liquid for AFM, time for image 0.1 to 1 minute, here 1 to 5 minutes. For horizontal resolution for SEM-TEM is 0.2 nanometer for TEM and 5 nanometer for FE-SEM, and 0.0 nanometer for AFM. Vertical resolution N by A, 0.05 A, 0.05 nanometer AFM. Next, field of view 100 nanometer TEM and 1 nanometer SEM. Here 100 meters, so that depth of field good. Here poor. Contrast on flat samples, poor, good. Each microscope is very different from another. SEM scans the surface of the sample by releasing electrons and walking the electrons. Bounce or scatter upon impact. The machine collects the scattered electrons and produces and the image. The image is visualized as a television-like screen. On the other hand, TEM practice the sample by directing the electron beam through the same. The result is seen using a fluorescent screen. SEM images are 3-dimensional, while TEM pictures are 2-dimensional and might require a little bit of interpretation. So materials when reduced down to 100 nanometer are called nanomaterials. The synthesis of nanomaterials can be done either by top-down or bottom-up approaches. The characteristic techniques like XRD determines the size and structure of the materials. FITR and UV wise spectroscopy determines the conformation of the bonds formed in the nanomaterials. TEM, SEM, and AFM determines the size, morphology, and the atom present in the materials. These we are studying in this particular third lesson. Next, block 1 complete. Next class we will discuss block 2, that is properties of nanomaterials. Electronic properties, dielectric properties, and magnetic properties. These three were studied in second block. Electronic properties of nanomaterials, dielectric properties, and magnetic properties of the nanomaterials we studied in next class.